Our next speaker is Tom Pagano. Tom Pagano is the project manager for the Atmospheric Infrared Sounder, the AIRS project at NASA's Jet Propulsion Laboratory, and is also responsible for the radiometric and polarimetric calibration of the AIRS instrument. He's involved in several studies and technology demonstrations for NASA and NOAA, including the CubeSat Infrared Atmospheric Sounder, CIRRUS. Prior to joining JPL, he was the chief systems engineer of the MODIS instrument Raytheon, which was formerly Santa Barbara. While at Raytheon in 1991, he was the project manager and systems engineer for the interferometer thermal sounder, ITS, which we've seen on prior slides yesterday, study for UW and UMetSat, and this is when he first met Hank, and he has worked with him over the years on AIRS, Chris, and sees him frequently at meetings, reviews, and conferences. Tom is a member of G6 and AMS and is a fellow of SBIA. Tom's talk title is Hank Revercomb's Contribution to Hyperspectral IR Sounding from Space, a NASA AIRS Project Perspective. Please join me in welcoming Tom.
Thanks, Joe. You know, Hank's done a lot for the NASA community. I'm going to focus here on the IR sounding part, not say a whole lot about Clario, although I do want to acknowledge that's a big part. I'm just not really well connected with that. So we'll just talk about AIRS and what I know mostly. So AIRS is the atmospheric infrared sounder, you know, we launched in 2002. Let me just go to the next slide here. It's one of several instruments that NASA has in their fleet of spacecraft. AIRS is on the Aqua spacecraft, and we have the, I guess I don't need this. I could stand over here, right? Okay. And we have the, of course, we consider the SWOMI NPP part of the NASA fleet. I think a good demonstration of NASA and NOAA collaboration. In fact, I think the AIRS project is a star example of NASA and NOAA collaboration, and it primarily is because of the relationship that the IR sounding community has had with NOAA over the years. So I'm going to tell you a little bit about the kind of products we develop. Here you have the Aqua spacecraft, launched in 2002, Vandenberg Air Force Base. Of course, it was a late launch at 4 in the morning, and it was not too spectacular up into the clouds, one of those usual launches. But on this satellite, I think I have most of my career wrapped up in here. We have MODIS up here, which I spent a lot of time working on. I came to Santa Barbara in 1985 and learned how to do systems engineering from Stillman Chase, who also has his regards. He wasn't able to make it, but I did call him and ask him, you know, for some information. But in any case, and also Dan Laporte as well. These were my mentors, so it's nice to actually have had an opportunity to work with some of the great minds in the industry. And but about the time we were waiting, we had written the Phase CD proposal, and we were going to, we were waiting for the award to decide if they were going to select us or not, or the competitor for MODIS. That's when I was able to support Wisconsin in the IS study, for interferometer thermal sounder study. So I'll get to that in a minute. I didn't know that AIRS was actually the name before it was selected, that there was actually a competition there. So I'm learning a lot from your history here. So this is AIRS over here. It's the atmospheric infrared sounder. It's a grating spectrometer. And I have to say that when I came to JPL in 97, this was when we had completed MODIS and we were going to be building VIIRS, and I wanted to do something different. They were going to move us all to El Segundo. So I came to Santa Barbara and started working on it was an interferometer of a different kind. It was a astronomical interferometer, a spatial interferometer, these giant two siderostats, they called them, that would look at distant stars and try to measure the wobble of a star due to the gravity. It was called SIM. And it was extremely ambitious. And you know, I'm the kind of guy who likes to figure out if this thing's going to work at all on my own. And I was kind of redesigning this and saying, well, I don't know, this is really ambitious. They needed to measure picometer path lengths over 10 meters, and it was a little bit too much for me to handle. So I said, I'm going to go back to my roots to see if there's anything going on. And I found George Aumann, who also sends his regards. And he gave me a job on the AIRS project doing calibration. I was a calibration team lead. And at that time, they were finishing the development of AIRS and started to, we're doing the final calibration on level 1B calibration pre-launch. And again, I'm looking at this instrument going, oh my God, because I had been looking at the FTSs for a long time, very simple detectors, simple optical system, and things seemed to work pretty elegant. And I go to Fred Callahan and I say, have you guys thought about this with an FTS? And I had not known anything about the history and the debates and the arguments, and he just looked at me like, oh my God. Almost. I think people have been patient with my naivety at times, but I appreciate that. And later on, he goes, I keep telling him, what about interferometers? They're great machines, and the data. He goes, Tom, a grating is a solid state interferometer. And I said, okay, I guess it's sort of like that. But it is a lot different. And I think one of the biggest differences and challenges we've had on the AIRS project is dealing with the over 5,000 detectors we have. I think it was, the AIRS instrument is amazingly well calibrated, and to most people who are actually involved in the retrievals, they don't care about detectors that are dead here and there because you've got so much redundancy in the spectrum. And I want to thank the scientific community for being so gracious, and when they see our ugly spectra, they really realize that that we're able to identify the good channels in there and don't look at the whole picture, just look at the channels, and it has been very good. And again, both Hank and Bill have come to our meetings over years, and I better get moving on because I have a lot to talk about here. So Hank has been a very important part of our science team, and Bill is from the beginning. And as you can see here, these are the rock stars of the community here. And Hank would come to our meetings, and he was a very active member in our team meetings. And the point I wanted to make with this slide is that he is still active in our community. And that's why I have this little excerpt here from the Earth Observer. This is our favorite magazine for the Earth observing system NASA people I know, but if you ever get a chance to get a copy of this, it's a great magazine. And he came to our last team meeting and gave a very nice presentation. So I appreciate that and hope you'll continue to come to our meetings. Even though you're retired, hopefully you'll still get a chance to come and join us. So the other main thing that I wanted to point out was that right after launch, we really had no visibility into the calibration accuracy of the instrument. And scanning his was a great tool for evaluating the instrument characterization. And to our surprise, the instrument was very well calibrated, 200 millikelvin radiometric accuracy. I was surprised they were able to get that kind of agreement aircraft in a satellite instrument. So this was probably the first of many satellite aircraft and satellite ground-based comparisons you've done over the years. And, we have not changed the calibration of the AIRS since launch. The changes that we would have made were too minor to really improve things, but we're at the point now where we have a new calibration for the instrument. I think the biggest change has been that the polarization of the mirror is better characterized now. What we have is in AIRS, and this may be true in the FTSs as well, that when the scan mirror itself introduces its own amount of polarization. And in the grading systems, we have the grading has its polarization, and the polarization from the mirror and the spectrometer tend to couple against each other. And when you look at space to do a calibration, it's not at the same angle as when you look in the Earth. So we've spent a lot of time trying to fix that and understand it. And now we've had some good data from our space looks. We have multiple angles in our space looks that we can use as sort of like a deep space calibration of our instrument. And we've been able to improve the calibration of AIRS considerably from what we thought before. So we'd like to get better validation again as well. Another point I wanted to make out about these instruments is that they're really remarkable in the fact that they scan full swath. They're global mappers. These are different than our high-resolution instruments in that they measure the whole globe every day, and this is true for Chris as well. What that has done, it's brought a unique type of data product to the data assimilation folks and NWP centers, and they found that not just the global coverage, but of course the hyperspectral part of this is really the unique feature that allows them water vapor and new information about temperature and vertical resolution that they didn't have before. So these instruments, as you've already heard, have had some of the highest impact. The infrared sounders, AIRS, Yazi, and Chris, have some of the highest impact to operational forecast. But that global coverage, again, enables us to, and I like to think of it like this, we're videotaping our planet from space in 3 dimensions. And that the time resolution isn't 30 hertz like normal video that we have here, but if you look at enough of these animations, they're really remarkable. The way you can see, here you're looking at the vortex, but this chart has a little bit more on here too. It also talks a little bit about our retrieval process. What we do with these radiants is we generate geophysical variables from these very complicated spectra. And we pull out, we have a table that at JPL and at NASA that we focus on minimizing the error between the observed and the calculated radiances. And that ends up with a final temperature and water vapor profile. And there are many different ways of doing this. I know Wisconsin has their own, and Joel Susskind has his, and NOAA has their own. But in the end, they all basically do the same thing in generating geophysical variables from the radiances. And there are a lot of geophysical variables that we can get out of these instruments. And when you think about it, and the fact that they all look completely independent of each other, these are the same, most of these are the same time period, but you're looking at all these different products from AIRS that we're videotaping. And what I think NASA realizes that this is a very, very important data set. And the decision to move to CRIS for continuity wasn't taken lightly. So I think we now have accepted that decision at NASA, that the CRIS is going to be the one to extend the AIRS record to the next 20 years or beyond. And so what we've done is spent a lot of time looking at trying to merge the 2 geophysical products. And we have Joel Susskind and Chris Barnett as part of our NPP, so we'll meet NASA NPP science team. And we're testing all different retrievals. So what we do at JPL is we test these retrievals and validate them against radiosondes and try to make sure that the data is going to be continued for a long period of time. And I think it's important to the entire scientific community because these instruments measure important variables related to global warming and climate change like water vapor. And what you're seeing here is a very old animation. I apologize, it's kind of low resolution, but you're looking at an isosurface of water vapor. So the purple is actually higher and you can almost see the relief in the image. But again, staring at these, it's just remarkable that these instruments are able to resolve these features and videotape these invisible things that we can't see on the Earth. But scientists, they don't care about the animations as much, but they like the data because what it allows them to do is to validate their climate models. In particular, we have over here in the upper right a comparison by a couple folks at Scripps, David Pierce. And what he showed was that when he compared a whole bunch of climate models to the AIRS data set, he found that certain regions, and this is sort of an ensemble of all the models, that most of the models tended to be wetter and in the upper troposphere and drier in the southern hemisphere, and in the northern hemisphere, drier in the lower troposphere, so that there was really a bias in the models. Now, that doesn't really matter to a lot of folks because the biases can be sustained without, and you can still do trending and evaluation of processes with the models. But it was important information to help the models balance, they have to have the right OLR, and they have series for the outgoing long-wave radiation, so they tend to balance the water vapor distribution to compensate, but it doesn't always turn out right. The other thing done that was very interesting was Andy Dessler at Texas A&M took a warm year and a colder year. Well, where's the water vapor going? And this was an effort to validate water vapor feedback. And he found that in the warmer years that the water vapor tended to be higher in the equatorial upper troposphere, so that, in fact, it would serve as like a blanketing effect. And he was able to validate the water vapor feedback with this data set. And the models pretty much got it right. So that what it means is that for every increase in CO2 of 1 degree, there will actually be 2 degrees, increase in temperature due to CO2 of 1 degree, there will actually be 2 degrees of increase in temperature because of the water vapor feedback. But again, these instruments are good for looking at trace gases and air pollution. We had Laura Pan and Dr. Pittman look at stratospheric tropospheric exchange. We did not realize that we had this much vertical information in our data sets for ozone, but it did help them identify that it's possible for ozone, that it's possible to detect ozone intrusions into the lower troposphere. And now that's important because if you're a regulator, you're trying to measure ozone levels in a city, what can happen is if there's an ozone intrusion, all the ozone levels will go up, and you want to be able to differentiate that from the actual ozone production on the ground. And so they were very interested from that. And so this animation on the right is just showing our ozone in the northern latitudes here, and in fact, you can see the transport of ozone with that. More recently, we've been looking at lower tropospheric water vapor and its the ability to predict drought. It turns out that atmospheric water vapor, relative humidity, is a better indicator of drought than many of the methods they're using already, like precipitation. And precipitation, it's kind of late, but we can get maybe 2 to 3 months advance warning on drought with the water vapor. So what we've done at JPL is develop these maps of vapor pressure deficit, and we're starting to provide those maps to the U.S. Drought Monitoring Agency so that they can evaluate them in predicting drought. It's great work done by UC Irvine. Other trace gases, SO2, sulfur dioxide. This is a map by Fred Prada. This was the very large European volcano that grounded air traffic. I think you may have remembered that back in the, I don't know when this was, a few years back. But what happens is the airplanes cannot fly through these plumes. It'll just destroy their engines, so they need this kind of alert system. So what we've done at JPL is taken the SO2 channels, brightness temperature channels, and we've developed an alert system on those brightness temperature channels, and that alert goes to the Volcanic Ash Advisory Council so that they can alert the aviation industries. There are several other methods for alerting for volcanoes. I know MODIS has them, and OMI has them. But AIRS is another data set that they need in order to validate everything. Okay. So upper right, you're looking at monoxide, and down here, you're looking at these giant plumes being developed by forest fires. How am I doing on time? Okay, great. And this was another plume that was generated by a fire that we had in Pasadena. Actually, this fire went this plume of carbon monoxide went all the way into the upper troposphere and was lofted all the way to Texas, where we actually found that the air quality in Texas a few days after the fire was pretty bad. So lots of uses for these hyperspectral sounders. The data this is an animation showing carbon dioxide, which is a very difficult product to retrieve. Dr. Mushaheen, before he passed, was very successful in making a mid-tropospheric carbon dioxide product. The interesting thing, if you watch, is as it greens up, you tend to see that there's less, it tends to draw down the carbon dioxide. So in the winter, the carbon dioxide builds up in the mid-troposphere, and then when it greens up, it seems to pull down in all these places. And we were actually able to show that there's a pretty good correlation between what's happening at the surface in the mid-troposphere, but there's phase lags because it takes a time for the CO2 to be lofted. And now, this is very interesting, but when Moose passed, we really don't have anybody to continue this work on the AIRS, and so I'd like to know if you guys have any ideas on that as well. But AIRS is not going to last forever. I mean, my goodness, it's lasted 6 years. We're very happy with that. It's a testimony to the incredible engineering team at BAE Systems and all their contractors. It's a good machine, but we do realize we don't have forever on this, and that's where the CRIS needs to pick it up. And so we're watching closely the calibration work that's being done here at Wisconsin. We're very pleased to see how well the calibration has come out. The AIRS CRIS comparisons are again within 100 to 200 millikelvins. We may get another 5 years out of the AIRS, and that's good for climate purposes. Having that overlap is really allowing us to do this comparisons. So that's again where I'm talking about CRIS. We go back a long time on CRIS, and we've been working together with Wisconsin for many years, but there was this big gap. I was the person who really was part of the CRIS team, but I ended up being part of the AIRS team, destined to be a sounder person. But I'm happy with that. It's been nobody stays on a project 16 years, but I'm really happy to have been part of this team. It's like family. And so, yeah, like I said, CRIS looks really good. I borrowed these slides from one of Hank's talks. He comes to team meetings and tells us how good CRIS is, and most of us smile and say it's great. So, and here's pictures of the CRIS on, here it is up here, the CRIS on JPSS. Great satellite, another high performance, high-end engineering, more expensive systems. And then also, there's been a lot of work done with AIRS CRIS comparisons and CRIS IASI comparisons and CRIS IASI and AIRS comparisons at Wisconsin. Please continue that work. We really appreciate it. Keep coming to our meetings and show us how it looks. And we're going to have a new version of Level 1B coming out, so we hope you'll go through one more iteration with your latest and greatest evaluations and tell us if it's any good. Another thing I wanted to tell you about is that, and I'll look out down here, is that NOAA came to me in 2015 and asked if we could do AIRS in a CubeSat. And I said, "Are you kidding?" And they said, "No." And so I went to my engineers and I said, "All right, guys, what do you got?" And they said, "Well, we got these little mini coolers, and we've got some new detector material that's really good, and we've got, so they came up with their all kinds of great ideas, and we said, well, maybe we can do something. But let me first say what the interest is and why the interest is there. These large satellites are very good and very high performing, but they're also very expensive. And while GEO is, I think, a great path, and I really want to support that more, the GEO really is the way to do the time resolution, because you get every 15 minutes or every hour. But there is the need for, these satellites are expensive. The LEOs have their own global coverage and provide data valuable to the NWP centers for assimilation. So they need them for improved timeliness, getting more times of day, gap mitigation. If one of these large satellites fails, what do you do? Maybe you could put one of these up to mitigate the gap. 3D atmospheric motion vector winds. We could potentially fly 3 of these satellites in a row and watch the images change, although it's going to be to demonstrate that. We've never done that. Atmospheric turbulence, potentially, and atmospheric chemistry. I think, this type you've seen all the gases we can get. There may be needs to focus on a particular gas and get that more information on that gas and get it at a better timeliness. So this is flexibility. It's just another dimension of how hyperspectral really can offer a wide variety of things. And so in order to, I started pursuing this in 2015. I wrote a proposal to NASA for the INVEST, and to build one of these things. And we actually won and started development, and we made a lot of progress on it. We developed the focal planes in our first lot. We have this new Hotbird detector material. It's a very, it's like Mercad in performance, but it's more uniform, so it allows you to operate at a few degrees warmer. We developed put it in with the filter, and we got the coolers and built our electronics, and we're maybe 4 or 5 months away from finishing the payload assembly. We had not bought our spacecraft yet, and we had our annual review and projected an overrun, so they canceled our project. The first thing I thought of was gifts, right? How really, when you're almost there at your 10-yard line from the touchdown, and you just want to bring it over the fence, you just need a few more bucks or something, and there's just some reason, political reasons or whatever, they just said, don't bother. But the good thing about this is that it's very low cost, and as easy as these things are to cancel, they are to get going again. So I'm hoping, I've got a few proposals in the fire, one of which is I'm trying to get the planetary people excited about this and maybe flying one of these around Mars. So I've got a proposal into the Matisse call to finish it. So hopefully they'll see the value in it. The way these things operate is they're spring-loaded and they just pop out, and everything unfolds. This is what our satellite would have looked like, or may look like someday. Lots of solar panels to run these coolers, and we have to cool the optics as well. And this particular instrument, just for a little more information, it operates from 1950 to 2450, so we get the CO2 absorption feature and then go into the water band. The spectral resolution out here in the CO2 region is comparable to AIRS, and it's not as good as CRIS down here or IAZI, but it should be satisfactory for temperature. And then we a little bit better than AIRS. Actually, AIRS doesn't cover this side of the water band. We cover the other side of the water band. And our analysis shows we should be comparable in the lower troposphere to about 400 millibars, maybe 300 millibars, and maybe do really good in the very lower troposphere, because the shortwave or the midwave, I like to call it, has good weighting functions down there. So we need to learn, as a community, we need to learn how to better utilize our midwave data. We have a lot of it from AIRS, we have it on CRIS, and so how do we use those sharp weighting functions to improve our lower tropospheric performance? And again, Wisconsin is here. They've helped us on AIRS. They're helping us now on this as well. I think I want to thank June Lee for helping us, and his team for helping evaluate the impact of these CubeSat sounders on performance. This isn't in the winds aspect, I don't believe, but the question is, can you get some mitigation of CRIS? Now, granted, the performance is not as good, but with a couple of them, you might be able to mitigate. So that was very helpful. So in summarizing here, I want to point out that NASA and NOAA satellites, and particularly the IR sounders, improve weather prediction and support Earth science. They're really valuable. Under Hank's direction, SSEC has been and continues to be a world leader in IR sounder development, calibration, applications, and science. We recognize that at JPL and NASA. And IR sounders, including AIRS, CRIS, and IAZI, have among the highest impact. Lots of applications. Aqua is expected to run out of fuel in 2022, and we are counting on CRIS to bring us into the next decade. And thank you for your work on that, because if we didn't have that, we would not have the beautiful data we have today. So they're interested in smaller satellites to save cost. This is something we can work on together, I hope. The CubeSat technology enables lower cost per satellite. Constellations may be an alternative to GEO, although I don't want to say, I would certainly rather have a constellation of GEO, I think. That would be the ultimate. And let's hope we can get that. And if there's anything we can do to help support that, I want you to know I want to help support that. We need to work together as a community. There's been many years of stone throwing. I think I sort of sat in the middle of this and dodged a bunch of rocks here and there. But I want to say that Hank has been very gracious in coming to our meetings despite some of the criticism, and has always been there to show how this instrument, the CRIS instrument, has done good, and AIRS has done good. You've been very positive. We really appreciate that. And I'm really looking forward to more collaboration now than we've had in the past. We need this relationship to continue as a community. If you look at many other communities and how they get what they want by just all getting together, I think that's kind of where we're at now. We're all really at the point where we're starting to speak the same language and speak the same, have the same interest and be really, really together. This is probably the best collaboration I've seen in the IR sounding in the history of the program. So thanks again for your support. Thank you.
Well, we have time for a quick question or two, if anybody's got it. Please, sir.
Hey, Tom, I thought that was very interesting that we're moving to the mid-wave. I assume that's, for size and cooler, optimization stuff. Is there a concern about the shortwave scattering? Is that something we're going to have to take into account, or is that you've looked at that and it's small enough? We don't care?
No, the technology, and that's sort of my it's easier to do, obviously, in the midwave and cheaper. And the question is, it's really a challenge for us. Like you say, we've got non-LTE to deal with, scattering, surface emissivity to deal with. I'm sure clouds, and so this is not an easy thing to do, and I by no means want to replace the long wave we have. The question is, assuming we have this fleet of operational sounders with the long wave and hopefully in GEO as well, can we throw up a few more of these things and get more data with that because they're cheap, and use that to get us some information. So it's not by any means a direction.
Yeah, my worry is that operational NWP centers want to assimilate radiances, and now they have to have in their forward model scattering, and that would be an interesting. We may have to push back to retrievals.
Well, that's a good point, and we need the help of the community to improve the scattering, the forward models, and to include scatterings. I know they are working in that direction already.
Thank you, Tom.
Thank you.
One more round of applause for Tom.